There is a black hole the size of 10 million suns tearing through empty space right now at 2.2 million miles per hour. It is not inside a galaxy. It has no home. And behind it, it is dragging a glowing trail of brand new stars, stretching 200,000 light years long, a trail twice the width of our entire Milky Way. When astronomers first saw it in their data, some of them genuinely thought their instruments were broken, because what this thing is doing should be physically impossible. Black holes are supposed to destroy matter. They swallow light. They crush stars. They consume everything nearby. So why is this one sitting alone in the cold, dead middle of nowhere, creating stars instead? And what force in the universe is powerful enough to throw something that massive clean out of its own galaxy in the first place? The answer to that question was just confirmed, and it changes more than what we know about black holes. It changes what we know about the universe we are living in. This story starts the way the best discoveries always do, completely by accident. In 2023, a team of astronomers at Yale University, led by Peter van Dokkum, were sifting through old Hubble Space Telescope images. They were not hunting for black holes. They were looking for star clusters in a completely unrelated dwarf galaxy. Routine, archival work, the kind scientists do constantly. Then someone noticed something in the image that had no business being there. A streak. A perfectly straight line of light, as if someone had taken a ruler and drawn a thin, glowing line across the darkness of deep space. Their first assumption was a cosmic ray, a charged particle slamming into the telescope sensor, something that happens constantly, and usually looks like a white scratch across an image. It is so common that telescopes routinely take multiple exposures of the same patch of sky, specifically to catch and discard these false signals. Check the next exposure. If the streak vanishes, it was a cosmic ray, move on. Except this one did not vanish. They checked the other exposures of the exact same patch of sky, and the streak was still there, in precisely the same location, pointing like an arrow at a distant galaxy system roughly 8.8 billion light years away. It was real. And that was the actual problem, because straight lines at this scale simply do not occur in nature. Galaxies form spirals, gas clouds scatter in every direction. Even plasma jets fired from black holes tend to curve and spread as they travel outward. Nothing in the universe draws a clean, perfectly straight 200,000 light-year line across a void. Nothing except something moving in a single direction at enormous speed for an enormous amount of time. With cosmic rays ruled out, the team worked through the alternatives one by one. Could it be a plasma jet fired from an active black hole? Possible. But jets at this distance rarely produce a signature like this one. Could it be a flat galaxy, seen perfectly edge-on, its disk lined up exactly with our line of sight, creating a thin streak of starlight? Also technically possible, but the shape did not match. The streak was too thin, too uniform, and the light profile was wrong for an edge-on galaxy. One by one, the mundane explanations fell away, and the strange one kept surviving. A supermassive black hole, somehow ejected from its home galaxy, tearing through intergalactic space and dragging a trail of gas and newly formed stars behind it. This exact scenario had been a theoretical prediction for over 50 years. Since the 1970s, physicists had calculated on paper that ejecting a supermassive black hole from its galaxy was physically possible under the right extreme conditions. But in half a century, nobody had ever found direct evidence that it actually happened anywhere in the real universe. It was the kind of prediction that sits quietly in textbooks, labeled theoretically possible, and then gets mostly forgotten, because the universe has never been generous about handing over clean evidence for its stranger tricks. Now, something that looked exactly like a runaway supermassive black hole was sitting in Hubble data, pointing directly at a galaxy 8.8 billion light years away. Hubble had shown them the streak existed. What they needed next was a telescope powerful enough to measure exactly what was happening at the leading tip of that streak. Because if this really was a black hole moving supersonically through gas, there should be one very specific signature waiting at its front edge: a shock wave. The same kind of pressure buildup that forms in front of anything moving faster than the speed of sound through a given medium. They needed the James Webb Space Telescope. Webb pointed its NIRSpec instrument directly at the tip of the streak. This instrument does not just photograph what it sees. It breaks incoming light apart into its component wavelengths and reads both the chemistry and the motion of whatever produced that light all at once. And what came back from a telescope orbiting nearly 1 million miles from Earth was dramatic. Right at the very front of the streak, the surrounding gas showed a sudden, enormous jump in velocity. 600 kilometers per second of speed change packed into an extraordinarily small region of space. That kind of sharp, localized velocity spike has exactly one explanation in physics. Something massive moving through that gas at supersonic speed, slamming into it and compressing it like a wall. The shape of the shock wave, the temperature of the gas, the geometry of the entire structure, everything pointed in the same direction. James Webb had just confirmed the first runaway supermassive black hole ever directly observed. Scientists officially named it RBH1, Runaway Black Hole 1, because the expectation now is that this will not be the last one found. Sit with these numbers for a second. A 600 kilometer per second velocity jump in the shockwave gas alone. The black hole itself is moving at roughly 1,000 kilometers per second, approximately 2.2 million miles per hour, about 3,000 times the speed of sound at sea level here on Earth. At that speed, this object could travel from Earth to the moon in about 14 minutes. It could cross the entire width of our solar system in a matter of days, and based on the length of the star trail behind it, it has been moving at this exact speed for roughly 70 million years straight. Here is the part that stops people cold. This thing is not simply flying through space. It is actively building something behind it, stretched across a 200,000 light-year glowing trail. Newborn stars, hundreds of them, actively forming right now, sparked into existence in the wake of a supermassive black hole that was supposed to destroy things, not create them. Understanding why requires understanding exactly what this black hole is tearing through. If a detail like that just made the universe feel a lot stranger, hit that like button right now, because the mechanism behind this is even wilder than the discovery itself. The space between galaxies is not actually empty. Most people picture intergalactic space as pure vacuum, nothing there at all. And compared to the interior of a galaxy, it genuinely is extremely thin. But it is not empty. An extremely diffuse gas called the circumgalactic medium fills the space around and between galaxies. Spread so thin you would never notice it moving through it at ordinary speeds. In most situations, an object drifting through this medium slowly would barely interact with it at all, the gas simply flowing calmly around it, like water flowing around a rock. But RBH1 is not drifting slowly. It is moving faster than the speed of sound in that gas. And when you outrun the speed of sound in any medium, something dramatic happens. The medium cannot get out of the way fast enough. In front of the moving object, gas piles up, compresses, and heats into a wall of superheated material called a bow shock, the exact same structure that forms as a wedge-shaped wave in front of a supersonic aircraft, or as a white wall of water at the bow of a speedboat outrunning the water's ability to flow around it. RBH1 is generating this bow shock at a scale that is almost impossible to visualize, a wall of compressed, superheated gas pushed ahead of a 10 million solar mass black hole moving at 1,000 kilometers per second. Then behind the black hole, the pressure suddenly drops. The gas that had been pushed, compressed, and heated finds itself in the wake, the pressure falling away, and it begins to cool. As it cools, it starts clumping together under its own gravity. When those clumps grow dense enough, after tens of millions of years, the pressure at the center of each one climbs high enough to trigger nuclear fusion. Stars are born, one after another, strung out behind the black hole in a 200,000 light-year thread of stellar nurseries. Stars with no galaxy to call home, born entirely out of the wake of an ejected monster. This is exactly what James Webb saw at the tip of that Hubble streak, and researchers confirmed it in late 2025, publishing their findings in the Astrophysical Journal Letters. Lead author Peter van Dokkum and his team described it as the first direct confirmation of a runaway supermassive black hole, identified through its supersonic bow shock. The question scientists have wrestled with Since that confirmation is not whether RBH1 is real, that part is settled. The real question is how something like this happens at all. What force in the universe is strong enough to kick an object weighing 10 million times the mass of our sun clean out of an entire galaxy? The answer is gravity itself, operating under conditions of extreme violence that only occur during galaxy mergers. Galaxies have been colliding since the early universe, and it is actually one of the primary ways galaxies grow. Our own Milky Way has absorbed dozens of smaller galaxies over its lifetime, and in roughly 4 billion years, it will collide with the Andromeda Galaxy. When galaxies merge, they bring their central supermassive black holes along with them, and those black holes, pulled together by mutual gravity, eventually spiral toward the center of the newly combined galaxy and begin orbiting each other in a slow dance that can last millions of years. There are two known ways this situation can produce a runaway. The first involves three black holes. If a third galaxy joins the merger, bringing its own supermassive black hole into the mix, the resulting three-body gravitational interaction becomes fundamentally unstable. Three massive objects simply cannot maintain a stable orbit together. The mathematics of gravity does not allow it. Instead, two of the three form a tight pair, and the third gets flung outward, carrying away energy transferred from that pairing, essentially a gravitational slingshot at the scale of entire galaxies. The lightest of the three is almost always the one ejected, sometimes with enough speed to escape the merged galaxy's gravity entirely. The second mechanism is stranger and does not require a third black hole at all. When two supermassive black holes finally merge, they release an enormous burst of gravitational waves, ripples in the fabric of space-time itself. The same kind of waves LIGO and Virgo detect here on Earth, from smaller stellar mass black hole mergers, but on an incomparably larger scale. If the two merging black holes have different masses and different spin orientations, the gravitational waves they emit are not symmetric. More energy radiates in one direction than the others, and in physics, firing energy in one direction produces a kick in the opposite direction, Newton's third law applied directly to the warping of spacetime. If that asymmetry is large enough, the resulting recoil kick can exceed 1,000 kilometers per second, more than enough to send the newly merged black hole flying out of its galaxy and into the intergalactic void forever. In July of 2026, a team led by Tusif Islam at UC Santa Barbara published a study in Physical Review Letters that worked the entire problem backward from RBH1's known speed and trajectory. Using numerical relativity simulations built on Einstein's general relativity, they reconstructed exactly what the original black hole merger must have looked like. Their conclusion was remarkably precise. The two original black holes had a mass ratio of no more than about 6-1. The larger of the two was spinning rapidly, with a dimensionless spin magnitude of roughly 0.75. The binary was precessing, wobbling on its axis as it spiraled inward, before the two finally merged approximately 70 million years ago. That specific combination of masses and spins produced a gravitational wave recoil powerful enough to launch the remnant at nearly 1,000 kilometers per second. Think about what that actually means. Scientists looked at a glowing streak of newborn stars in an old Hubble image, confirmed it with James Webb, measured its speed and geometry, and then ran the physics backward through Einstein's own equations to reconstruct the exact properties of two black holes that merged 70 million years ago in a galaxy 8.8 billion light years away. They can tell you how fast each one was spinning. They are reading the ancient history of a cosmic collision directly out of the wake it left behind. If this level of scientific detective work has you hooked, subscribe to this channel and turn on notifications right now, because there is a genuinely unsettling twist still coming. Researchers point out that mergers, like the one behind RBH1, are exactly the kind of events the future LISA mission, the Laser Interferometer Space Antenna, the European Space Agency's planned gravitational wave observatory, is designed to detect directly anywhere in the observable universe. The team calculated that a merger like this one would produce a gravitational wave signal in LISA with a signal-to-noise ratio exceeding 1,000. These are not faint whispers in the data, they are shouts. And here is the part of this story that genuinely carries the most weight. RBH1 was only visible because it happened to be flying through a patch of circumgalactic gas dense enough to actually light up. The bow shock at the front, the star-forming trail behind it, all of it depends entirely on the black hole having something dense enough to slam into, something that produces visible light and measurable gas signatures readable by telescopes like Webb. Van Dokkum and his team were explicit about this in their paper. If this exact same black hole were moving through a sparser region of intergalactic gas, there would be no shock, no trail, no streak in any Hubble image, nothing at all. We would have absolutely no way of knowing it was there. Not just hard to detect, genuinely, completely invisible to every telescope we currently operate. And that is what makes this so significant. Galaxies have been merging for over 13 billion years. The conditions that produce runaway supermassive black holes, whether through unstable three-body interactions or asymmetric gravitational wave recoil, are not rare exotic edge cases. They are natural byproducts of how galaxies form and grow. If ejections like RBH1 are a predictable outcome of galaxy mergers, and the physics strongly suggests they are, then this cannot possibly be the only one. There should be others, many others. Black holes of 10 million, 100 million, even a billion solar masses, launched from their home galaxies at extreme speed, currently crossing intergalactic space with no visible star trail to give away their position. Dark, silent, completely invisible. The universe may already be full of them, and we would have no way of knowing. The researchers who confirmed RBH1 flagged this directly as the next urgent problem to solve. They noted that the most powerful tools for finding more cases are the Wide Field Survey telescopes either currently operating or about to come online. The European Space Agency's Euclid telescope, which has already cataloged over 1.2 million galaxies in its first year alone, is scanning the sky in a way that could reveal the glowing trails of more runaway black holes, if they happen to be moving through visible gas. And NASA's Nancy Grace Roman Space Telescope, which completed construction in late 2025 and is preparing for launch, has a field of view 100 times larger than James Webb's, with the sensitivity needed to search enormous swaths of sky for exactly this kind of linear feature. Van Dokkum specifically named Roman as one of the instruments capable of turning this single confirmed discovery into a genuine population study. How often does this actually happen? That is the question everyone in the field wants answered next. That question matters for more than curiosity's sake. Right now, we have confirmed exactly one runaway supermassive black hole, and this confirmation only happened because of a genuine chain of coincidences. The object happened to sit in old Hubble archival data. Someone happened to be scrolling through images of a completely unrelated target and happened to notice a strange streak. That streak happened to sit in a region of gas dense enough to produce a visible trail. James Webb happened to be operational and available for immediate follow-up. Change any one of those conditions, and RBH1 would still just be a theoretical prediction sitting quietly on a chalkboard. So how many are we actually missing? If even a small fraction of galaxy mergers across 13 billion years of cosmic history produced ejected supermassive black holes, the true number could be staggering, with most of them currently sailing silently through the emptier regions of intergalactic space, completely undetectable by anything we have ever built. Our entire model of how galaxies work has been built around the assumption that supermassive black holes stay anchored at the center of their galaxies, that the relationship between a galaxy and its central black hole is permanent and fundamental. The confirmation of RBH1 does not destroy that model. The overwhelming majority of supermassive black holes almost certainly do stay put, but it adds a genuinely new category of object. Black holes that got evicted, that are out there right now, homeless and invisible, having abandoned their host galaxies tens or hundreds of millions of years ago. Before you go, tell me in the comments below how many more of these runaway black holes you think are out there right now, completely undetected. And if this story genuinely made your brain do something uncomfortable, share it with someone who needs to feel that too, because this is what the universe actually is, not the calm, steady thing you see in textbook diagrams, but galaxy-scale violence, black holes thrown clean across the cosmos, and stars being born in the wake of something that was only ever supposed to destroy. There is nothing chasing RBH1. There is nothing slowing it down. There is no galaxy waiting to catch it on the other side. It will simply keep moving faster than almost anything else in the known universe, out into the void, possibly forever. And somewhere out there right now, there are almost certainly more of them. Dark, invisible, moving, and we are only just beginning to build the instruments capable of finding them.